Welcome back to week 1, part 4 content. This is course on privacy and security in online social media. What we'll cover today is looking at some ideas about basics of graph or social networks also. But before that, if you have any questions, any clarifications, comments, feel free to post it on a mailing list again. So here is one idea that I think is phenomenally influential in terms of thinking about social networks. So this one is called as 6 degrees of separation. You may have heard this in different words. Next slide actually will tell you what are the other ways to refer this. But this is 6 degrees of separation. Essentially what it shows is that what the idea is that if you take any 2 random people in the world, let's take you and somebody who lives in, let's take Kenya or Australia or wherever, the hops between you and them will be 6. Right? So that's the idea here. So if you look at here, from start, somebody in Kansas goes to Iowa, goes to near Illinois, then Kentucky, then Pennsylvania, and then finish. This is showing an example of Tennessee, and then Virginia, and then New York, and then finish, right? So this is showing for the example in the US, but the idea is that the connection between 2 random people is actually only 6. Very interesting to see that it's so small. So this is also called as 6 degrees of separation. The slide basically talks of random person and you. It's a small world phenomena. It's referred as small world phenomena because just imagine, right? Any 2 random people in the world, there is some connection between 2 of us. Interestingly, the way that this experiment was done a long time back, but the way it was done was you will write a letter to these 10 people, and then those 10 people will write a letter to another 10 people, and then to figure out when this letter will come back to a person who's already gotten the letter before, right? So that's the way this experiment could be done. And this experiment was done to understand the hops between people. Right? This is also called Milgram experiment, 6 handshake rule, right? The question that I have for you is to think about if the same thing was to be done on Twitter, right? Or think of it as even on Facebook, right? Or Twitter, any of these platforms. What would this number be? Would it be less than 6? Would it be equal to 6? Would it be greater than 6? Right? Because I think if you understand this question and figure out an answer, or at least roughly think of what the answer could be, then I think you're understanding the idea also behind the 6 degrees of separation and the way it works in social networks, right? So next idea. So the ideas are written here. The next idea is called strength of weak ties. I think this is another phenomenally influential idea in social networks, which is strength of weak ties. The idea here is that the information that flows or the opportunities that you get is generally from weak ties compared to strong ties. Right, so you just look at this graph. The strong ties are drawn as a straight line. The weak ties are drawn as dotted lines, right? Which is basically somebody whom you meet in the train, somebody whom you sit next to in the flight and travel, somebody whom you just heard a lecture at some point in time, right? These are all weak ties that you can think of. Whereas somebody who you're doing BTech program with for 4 years, or somebody who is in your school, or somebody who is neighbor at your home, all of them are strong ties, right? So that's the difference between a strong tie and a weak tie. And the idea, the proof that they had is to show that the power of weak ties is very high. I'll show you some more examples and this paper is actually one of a very popular paper called Strength of Weak Ties, which shows the importance of the weak ties. Also, just think about it, right? If you just pause the video for a second and think about where all the weak ties has played a role in your own decision making, you will be amazed at where all these weak ties have played. Some uncles, relatives, person who works in the office would have told some information, would have flown to your parents, and your parents would have given you some advice on doing something, and that would have helped you a lot. I know some of you may even tell about this own program that you're taking, BS, how you got to know about it, right? Today, weak ties could also be somebody whom you are just connected on LinkedIn, right? It could be that, connected meaning they are not really people that you may know. For example, some of you may be already connected to me on LinkedIn or Twitter. That's just a weak tie, right? You just got to know a professor who's probably teaching a course that you're interested in. You just clicked and linked connection. I also accepted the connection. The link is, I posted about let's take an internship opportunity at IIT Hyderabad, and you actually apply to that internship and get it and come to IIT Hyderabad, and it just changes your life, right? So that's what the strength of weak ties are, right? So this is what the actual paper talks about. So the line that I wanted to bring your attention is, I will refer to a tie as a local bridge of degree n if n represents the shortest path between 2 points. In figure 2a, AB is a local bridge of degree 3, in 2b a degree of 13. As with bridges in a highway system, a local bridge in a social network will be more significant as a connection between two sectors, to the extent that it's the only alternative for many people, right? So essentially what they're trying to say is that this is a local bridge. That's a local bridge, right? So these local bridges play a very, very strong role in many things. We'll actually see more ideas about how to measure these values, how to add quantitative information with these nodes that can help. So that's the idea. Again, strength of weak ties. I would actually love to hear from you either on the mailing list or email me about any of the incidences that has happened in your life, strength of weak ties. I mean, I have innumerable number of examples in my own life where the weak ties has played an important role. And sometimes I don't even know them very well. I can't even remember many times who's the person who played the significant role in my decision making, right? So that's the real paper. That's the actual paper, which is written by Granovetter, Strength of Weak Ties. Please take a look at it if you're interested in more reading the theoretical side of the paper. And we can also discuss the paper if you're interested. More ideas that we need to know before we get onto the content of the course in detail about, okay, let's collect the data. For example, earlier parts of this week, I actually mentioned about collecting data from Twitter, right? So if you collect the data from Twitter, it's going to look something like this. If you collect the data from Facebook, it's going to look something like this. What can I make sense out of this image is the question that we'll be asking now. What is a node? What is an edge? What is a node centrality? What is a degree centrality, betweenness centrality, and closeness centrality? These are all ways by which you can actually think of measuring the network strength, measuring the value of a node in a network, all that. Homophily, what is an homophily? What is a power law 80-20 principle? What is a scale-free network? What is a random network? All of that, we look at it. Again, this is not a social networks class, so I'm not going to go into detail about a lot of these measures, metrics. I'm using only certain words here because these we will end up actually using later in the course. And the papers that we will end up reading as part of this course also will have some of these words. Let's look at what a node is, right? So this is imagine if this was a network of people and the edges are just, let's say, friends in Facebook, followers in Twitter. So this is PK, this is probably you, it's another friend, another friend. The nodes are this graph, the way I'm representing these nodes are users. The nodes could be a YouTube video, the nodes could be a post, right? The nodes could be you're taking this class in the BS program, and all the students are actually nodes of the graph who all are taking classes together can be also captured in a graph, right? So then you can be the node and the course could be the edge, the course could be the node and the students could be the edge. You can represent the graphs in many different ways, right? So edges are also there. The types of links, right? The types of links, one is undirected, which is Facebook, because Facebook, the way it works is that I send a friendship request to you and you accept it and therefore we become friends. Right? So it's just both sides. There's not necessarily that, meaning another way to think about it is you can actually say that this is like that, right? We're following each other, right? So the undirected graph is a relationship where it is like a Facebook relation, whereas the Twitter graph, you need to mention. So if in Facebook I just say that I'm friends with you, describes everything as in the edge. In Twitter, there is, I follow you. You have to actually follow me back. Only when you follow, that edge is also getting created. If you look at this, the A person is following B in this, and B person is following in this. Whereas in this case, A is following C, but C is not following back A. Right? The direction is important. For example, a direction could be faculty and an advisor, faculty and the student part of the class. Right? So that's what a type of links are. So one way is undirected graph and a directed graph. There are many again, right? Many other forms of way in which you can represent this links. But for this part of the course, this much is enough. Okay, let's look at node centrality. Node centrality, there are three different parts in which a node is basically, as we said, node is just this, right, in the graph. And now we look at measures of that node. How all can you measure, right? So, for example, one way to think about it is who is most influential in a given graph, right? If I give you all the students who's taking this class, who's been the most influential person, let's take in the mailing list. Who's been most active? Let's take, if I draw all the students of this class as a graph, all of you are nodes, and edges are questions somebody asked and somebody responded. If we draw the line slide, then we can actually measure who was most active in the mailing list. Right? That's a very, very clear example that we can actually talk about. Right? So that is one metric that you can think. The other metric is that other types of metrics would be, one is just influential. Influential also can be defined in multiple ways. People just who are connected to them, and their other properties could be used to the properties of the nodes, properties of the person in that node can be used to define influential nodes also, right? Those are the things that we'll see. Three specific things that we'll see in this is called degree centrality, betweenness centrality, and closeness centrality. We've tried to keep it really simple. I think the idea here is only for you to get a sense of what these metrics are. So when we refer in the course later, you'll be able to understand what it is. Degree centrality. Here is a graph. I think it's a simple graph where people are connected to each other in different ways. Degree centrality assigns an importance score based on the number of links held by the node. What it tells us is that how many direct one-hop connections each node has to other nodes in the network. So it's essentially telling you that how many people are connected to me. In degree centrality, you can think of, you can break this also into in degree, out degree, all of that. But for now, simplicity, let's just look at degree centrality. Right? So there are these nodes, and you can think of as moderate degree centrality is all this green. So the users are Mary, Bob, Alice, Raphael, Elgar, Frederica, Jam, Aldo, Stefan, and Perry. We will just use this in all the three metrics. Same graph, we will use it in three different metrics to measure the centralities. And moderate centrality is the Raphael. In this case, Alice is the one which has the most number of edges connected. If you look at it, 1, 2, 3, 4, 5. Raphael has 1, 2, 3, 4. Right? So that's how you measure the degree centrality of the user. And of course, this degree centrality makes a lot of sense in terms of finding out who has the most number of connections in a network, right? Take a Twitter network of you and your friends, or let's take celebrities on the Twitter, and you can find a number of people connected to them. Okay, degree centrality. If you look at that's just a mathematical representation, what we just did, right? Number of edges that are connected to the node. Right? Simply, if you see Alice has 5, we calculated Raphael as 4. So similarly, all scores are written here, and you find the scores, put it in descending order, and find the maximum. That will give you the top node which has degree centrality. Right? Node which has the highest degree centrality on the top. But of course, you don't really need the top one always, right? You want to say, okay, who are the top 3 influential students in the class? Who are the top 3 influential top 3 users who are connected to more number of people who are talking about NPTEL right now, right? Think about the question: if NPTEL wants to actually find out the people on social who are talking about NPTEL, or people on social who are talking about this BS program, IIT Madras, right? All of that, if you think about it, can be measured with this metric called degree centrality. Let's look at closeness centrality. Closeness is a measure of average shortest distance for each vertex. Vertex is again an edge to each other vertex. Specifically, it is the inverse of the average shortest distance between the vertex and all other vertices in the network. Vertex is a node. So if you think about the graph again, it's the same graph, right? It's the same graph network that we saw before. Closeness can be used to find influences in a single cluster. Yeah. Again, this is going to help. So in this case, if you see, Raphael has the highest closeness centrality and Alice has the moderate closeness centrality. Let's go back and show you the earlier one. Alice is here. Raphael is here. Right? We said Alice has the highest degree centrality, whereas in terms of closeness, Raphael has the highest closeness centrality. Right? So again, there are different scenarios where you will use these different metrics for finding out. So here is how you will find out here is how you will measure the closeness centrality. Again, there's different ways you can think of it. One is just putting as inverse. The other one is n minus 1. So if you go look at the definition here, it says it is the inverse of the average shortest distance between the vertex and all other vertices. In this example, we have put as n minus 1. Again, it is, so this 9 could be just 1. So it will all be just the same. The value will be calculated anyway in the same way, right? Let's look at the way we can actually get this value, right? So if you look at, so now we'll do from distance of Mary to destination, right? Okay, Mary is on the top left. We'll start from here, okay? Distance of Mary to destination, right? The destination is E. E means Elgar, Alice, all the names that we have said, that is there, right? So let's go back. So we have to find the distance between Mary to Elgar. Mary to Elgar. So that's 2, right? That is 1, that is 2, right? So that's how you will calculate all of this. So Mary to Alice is just 1, right? Mary to Alice. Yeah, Mary to Alice is 1, Mary to Frederica, right, is 2 because it is 1 here and then 1 here. Right? So that is 1, and then this is the second one for Mary to Frederica. So you'll keep calculating each one of them. I mean, these are all, you don't have to do it manually for teaching this class, for you to understand what it is. I'm doing it manually, but there are programs which can easily calculate all of this by just a single line of code, right? So destination, so you will calculate. So this is a total of 22, right? Mary, if you see, that's a total of 22. And n minus 1, total number of nodes on the graph is 10. So n minus 1 is 9. So you'll get 9 by 22. Similarly, if you calculate for all of them, and the highest value is for Raphael, and therefore Raphael has the highest closeness centrality. Right. So that's how you will calculate closeness centrality. And in this closeness centrality, the idea is that can be used to find influencers, because Raphael is the person who is close to the maximum number of people in the graph, right? Because we were calculating the number of edges, right? So he's the node which is very close to most amount of nodes in the graph. Okay. Hopefully that helps, but if you need any further clarifications, we can talk about it later again. Please come to the office hours. I'm happy to actually interact with you in the office hours also. I keep saying about mailing list, but let's also try and make use of the office hours. I will try and have office hours on demand, or we'll set up some regular time slots where you can come and ask questions of the content of the class. Next is this betweenness centrality, where the betweenness centrality is, again, if you look at this same graph, now we are trying to calculate what the betweenness centrality is. Betweenness centrality measures how often a node occurs on all shortest path between two nodes. Right? We are thinking of shortest path between two given nodes. What it tells is, it shows which nodes are bridges between nodes in a network. So I'll give you another way to think about or understand what is a betweenness centrality. Betweenness centrality is somebody who plays a very significant role in connecting multiple subgraphs or multiple networks. For example, I would think of myself as a person having more betweenness centrality if I were to draw the graphs of people, faculty and students in IIT Delhi and IIT Hyderabad. Because I have spent time in IIT Delhi and I'm here, so if there is to be some information, some connection needed between these institutes, it will be best to go through me, because I'll have people known from both sides. That's the idea that you have to think about for betweenness centrality. So again, if you calculate the betweenness centrality for this graph, Raphael would be the highest. Let me walk you through how you would actually calculate the betweenness centrality. this is how we'll calculate betweenness centrality. This slide is a little dense. Let me walk you through how, what all it has, right? So essentially what we want to find is that given a graph, you want to find out edges between these two, right? So that's what this is there. So you want to find out every single node is written here, every single node is written here, right? And the values in each cell is the shortest path between the two in the row and in the column, right? So for example, this one is the shortest path between Mary and Elgar is just 1. Okay, shortest path between Mary and Alice is 1. That's what is written here. We have seen the shortest path in this case, Mary and Alice is just 1. That's what is written there, right? So shortest path between Mary and Jane, Mary and Jam is actually 3, right? Shortest path could be 1, right? So 2, 3, 1, 2, 3, right? So you can have, and then there could be, there's also 1, 2, and 3, right? So these are the shortest paths between Mary and Jam, but there could be also longer paths, right? So for example, you could go from Mary to Alice to Elgar to Frederica to Jam. So that would be 1, 2, 3, 4. So if you take the total number of paths between Mary and Jam, there's actually 4. In terms of the shortest path, which has 3 edges, right? So you use only that shortest path here. That's what is written here. You do this for every combination of the nodes in the graph, and you get these values, right? So that's what the cell value is. So the next one, so what is the question that we are calculating? We're calculating the betweenness centrality for Raphael. Okay. That is a fraction of the shortest path nodes that include Raphael, right? Because betweenness centrality, I said I have the betweenness centrality between Triple ID Delhi and Triple ID Hyderabad. You need to figure out all the edges that are going between me, right? Where I should be part of the shortest path. So now we are calculating the betweenness centrality for Raphael. So betweenness centrality for Raphael is the ones which has Mary, Elgar, Alice, and Frederica. So if you see, that's what is highlighted. That's the second part. Highlighted ones has Raphael. So yeah, and let's go back. You don't need Aldo, Stefan, and Perry, right? Because there's no Raphael connect. Raphael is connected to Aldo, but the shortest path is not, you will not go from Stefan to Aldo through Raphael. That's what is removed. Those are the ones that are white, right? Raphael you don't need to do, and then Aldo, Stefan, and Perry. That's the last 3 ones which are in white. So the highlighted ones are the ones where we have Raphael part of the shortest path. Therefore, it has Mary, Elgar, Alice, Frederica, Bob, and Jam. Okay. Then use the path which has Raphael, right? Now we have to find out. So there were 3 paths between Mary and Jam, right? So let's go back. There were 3 paths between Mary and Jam, right? Mary, Alice, Raphael, and Jam. Mary, Bob, Raphael, and Jam. Mary, Alice, Frederica, and Jam. So now there were 3 parts. If you look at this, there were 3 parts here, but only 2 has Raphael in it, which is Mary, Bob, Raphael, Jam, Mary, Alice, Raphael, Jam. Okay. So now that's what is calculated here. So now we calculate the Mary and Jam here. So we calculate 2 by 3, in which Raphael was part of. Then you do the same thing between Mary and Aldo, where Raphael is Mary and Stefan, Mary and Perry. For the where Aldo is, you will get these values. So it is organized in the same way. First is Mary, then you do the same thing for Elgar, Alice, Frederica, Bob, and Jam. If you calculate this value, it should be 20.16. So you can do this for every single node in the graph and calculate the betweenness centrality. Okay. So that's how you would calculate. Again, I mean, we don't have to do this for every user every time manually. There are methods to easily do this. But for the benefit of the class, you want to know how the program is also written, right? You may end up actually calling a function which does this, but you need to understand what is going behind. That's the reason why we kept it this way. And we'll actually also give you some exercises where you can actually try out calculating these values as we discussed in the slides. Now let's go to the next idea called homophily. So homophily is also an interesting idea because so if you look at this graph, right, on the left, the idea is that people, birds with feather flock together. So the idea is that can you actually find ways of which, if you are a, so to say, a cricket lover, you will end up getting more and more closer to people or connected to people who are also cricket lover. If you play tennis, there's high probability that you will get connected to people who also play tennis, right? So that's what this graph is showing. So if you see the blues are not connected, let's take if this was August 2022, this is Jan 2023, right? And this blue graph, user was not connected here. Eventually, they are all same type of people, so they will get actually connected. I'm sure you will see, let's take social example itself. In Twitter, again, you may not have followed me at some point in time, right? You started following me when we started this class, right? Because I'm teaching this class and you're interested in this course. Homophily, right? Some sort of, and possibly that the students in this class are also connected to each other. We will actually get you to share your social media handles, and we can actually get you to connect each other also at some point in time, right? So that is homophily. Homophily is the idea of birds of a feather flock together. And the opposite idea, right? There is a chance that people, opposite of homophily, people who are not connected, right? The heterogeneous people, which is called heterophily, or intermingling is opposite, right? So homophily is the same set of people coming together. If you see, it is homogeneous network, they say. They all look very similar. Heterogeneous network is people who don't have very similar, so to say, characteristics, features, right? So that's what heterogeneous network would look like. Let's move on. I think this is also another interesting set of metrics about networks. So this one is called as exponential as power law. So let's take two examples, right? One is an example of a highway, and then another is an example of airports. Right? These two are the examples of we look at in this graph. The degree of a random network follows a Poisson distribution rather than a similar to a bell curve. So I think let's leave the, I mean, if you understand statistics and these distributions, you will get the idea. But for the purpose of this class, I think what you need to know is that the networks that are that is like this, which is like an highway, right? Where every city, right? Every city will have a highway. No city will be left out not having an highway. When I compare it with the airports, you will understand what is that I'm trying to get across. But for now, keep in mind that the highways, you want to construct highways for everybody to use, right? The national highways in India, if you see, it is going breadth and depth of the country, right? You want that kind of network for people to be using it. But on the other side, right, in a network that is power law, in a network that is, which is like an airport, the way it will work is that You create airports in places where there are necessity for people to go, or people who are actually traveling more to those locations and doing things there. For example, Delhi, Bombay, Hyderabad, Bangalore, right? So you will put up airports, whereas some parts of the graphs get more denser. That's what will be a power law. Other way of looking at it is that the text that is written in a network with a power law distribution, most nodes have only few links. These numerous small nodes are held together by a few highly connected hubs. The idea again is that this is also called as 80-20 principle. There are many other ways to actually say the same idea, which is small proportion of nodes in a graph have more influence. You take Twitter, it's only a small proportion of people who actually influence rest of the people, or even create content. Influence secondary, create content, right? Even in a class, if you see, for example, even in our own class, if you see there are X number of students, there's only 20% of the students, less than 20% of the students will be asking questions, who will be active on the mailing list, will probably ping me and ask me questions about the content in the class. So that is the idea of power law, which is a long tail. Lot of people have small interactions in the class. Very small people have a lot of interactions in the class. Lot of people generate few tweets. Very small set of people create a large number of tweets. Okay. That's the idea between exponential and a power law. Here is another idea that we need to keep in mind. Again, these, I mean, if you're interested, feel free to go take a look at the references that I've put here, or take up some book on social network analysis. You should be able to get all of this in much deeper. But for the purpose of this class, we'll do some simpler ones. Clustering coefficient. Here is another idea. Clustering coefficient is an important concept to understand, so you will be able to appreciate what a sparse network is, what a dense network is. Which is, what is a sparse network? Which is that, look, how people are connected in the graph. Are they all very strongly connected? Many people are connected to many others, or they're loosely connected. Some people know some people in the graph, but not everybody knows everybody. Not necessarily everybody. More people know more people in the network. Very simple. So the first one is local clustering coefficient, which is you're just calculating it for a node. In this case, if you see the clustering coefficient of an I node, which is one node here, is the number of triangles connected to the node I and the number of triples centered around the node I. Right? So if you calculate this, you will get clustering coefficient for that particular node. So in this case, if you see there are no triangles in this network, so it's 0, whereas if you see here it's one triangle, so you get 1 by 6. Two triangles here, so you get 2 by 6, so you calculate it that way. Right? So interestingly, this clustering coefficient will come later also, looking at, let's say you collect a Twitter network graph and then you want to actually find out whether my network is dense. Because if network is dense, you want to use different properties, different methods to diffuse content, to actually get influences from that network, all of that. Global clustering coefficients, number of closed triplets divided by the number of all triplets open and closed, is the global clustering coefficient, which is, if you just think about it, what is the difference between open and closed? Or the way to think about it is that it is not a closed triangle. That's what we are trying to say. I'll show you an example in the next slide. Global clustering coefficient is that if you take 1 here, right? There are triangles that you want to think about, is that if you think about total connections, right? So, 1, 4, 3, right? 1, 4, 3 is a, 1, 4, 3 is a triangle. 1, 3, 2, 1, 4, 2, yeah, 1, 1, 3, 2, 3, 1, 2, sorry, 3, 1, 2 is a connection, right? It's not a triangle. And then 1, 4, 2 is also a, right? So that's the difference between a triangle closed, which is in this example, triangle closed is 1, 4, and 3, right? So that's a triangle closed. Here what we're looking at is that where all the edges, so this one has one here, and then one here, right? So 1, 4, 3, 1, 3, 2, and 1, 4, 2. That's the triplets for the node 1. If you draw this, meaning if you find this for each and every, so we've written it here for 1, 2, 3, 4, 5, 6, 7, you will get the total number, which will be 20 in this case. So that is how you will calculate global clustering coefficient. One thing to go back is that it is 3 into the number of triangles. If you take for 1 number of triangles formed, we have to use that 3 into number of triangles that we get divided by the total number of triplets, that is it. Number of triangles is that it's 1 here, first triangle, second triangle. Right? There are only 2 triangles with the 3 edges, right? And therefore it is 3 into 2 divided by 20. Let's go back to the formula again. 3 into number of triangles in the graph divided by the number of all triplets. That is 20. In that triplets, you use the triangles and the non-triangles also, which is what it says here, open and the closed. Okay, hope that helps. Again, the idea here is to find out how closely connected the network is, how loosely connected the network is. Example, just to look at, this could be called as a very dense network. This could be called as a very sparse network, right? Very densely connected, all nodes are connected, very loosely connected. Not that loosely connected, but definitely loosely connected compared to this. If you calculate the clustering coefficient, okay, that's another point. If you calculate the clustering coefficient of this, let's take if this is A and if this is B, A will be greater than B. The more the clustering coefficient is, the more the denser the network is. Okay. That's what I had for this part. With this content, we will wrap up the week for week 1, part 2 content. And if you have any questions, feel free to ask in the mailing list. And of course, come to office hours also. Thank you.